Every intersection on a coordinate plane acts as a visual record of a hidden algebraic identity. We must look closely at how these curves collide. By combining a graph's shape with its known maximum degree, we can reverse engineer the specific factors that define the function. Take this degree 6 polynomial. It features 3 distinct intercepts at -2, 0, and +2. These locations equal 0, providing primary evidence. To translate these collisions into an equation, we categorize the geometric behavior at each point. The local shape at an intercept identifies the structural factors of the polynomial. By reading these shapes, we can map out the exponents required for the equation. In algebra, an x-intercept is called a 0. It is a real root where the function's output hits the baseline. When we find a 0 at a coordinate like x equals a, we know the polynomial contains a factor of x minus a. The complexity comes from the multiplicity, the power or exponent attached to that factor. Multiplicity dictates the physical behavior of the graph. It determines whether the line slices through the axis or interacts with it in a more complex way. As multiplicity increases, the graph tends to flatten out or reflect away from the axis, rather than simply passing through. This gives us a direct method for deduction. Identifying the collision geometry allows us to determine the multiplicity of each factor. We'll begin on the left side of our graph at the intercept x equals -2. The curve passes through the axis with no visible distortion. This straight crossing indicates a single-order root, meaning the factor has a multiplicity of 1. Moving to the far right, we see different behavior at x equals 2. The curve touches the axis and immediately bounces back, creating a parabolic shape. A reflective bounce requires an even multiplicity, restricting our exponent options to 2, 4, or higher. These two distinct geometries, the straight crossing and the bounce, provide our first two exponents, a power of 1 and an even power. The final intercept is at the origin, where x equals 0. The line crosses the axis here, but it flattens into a twisted S shape as it passes through. This inflection crossing indicates an odd multiplicity greater than 1, such as 3 or 5. We can narrow these choices down using the degree of the polynomial. We were told this is a degree 6 function. Mathematically, the sum of these individual multiplicities cannot exceed the total degree of 6. The sum of our 3 multiplicities must equal 6. If we assign a multiplicity of 5 to the origin, the sum reaches 6 immediately, leaving no room for the even root we identified at x equals 2. To reach a total of 6, we must use the combination of 1, 3, and 2. This gives us the structural factors of the function. While we have identified the factors, the lead constant a remains unknown. Geometry reveals the bare skeleton of the function, but hard numerical data is required to determine its exact scale. Not every graph has a visible root for every degree. Sometimes the arithmetic of intercepts doesn't tell the whole story. Consider this degree 4 polynomial. There is only one visible intercept, and it occurs at x equals 2. The curve bounces off the axis at this single location. Since it's a bounce, we know the factor x minus 2 must have an even multiplicity. With a total degree of 4, we need to determine if this single root accounts for the entire function. To verify this, we have to look at the wider shape of the curve. There is a subtle bend in the curve high above the axis. This suggests a complexity that contradicts the shape of a simple power 4 function. By overlaying a true degree 4 graph, we see the widths do not match. A true power 4 bounce is flatter and wider. Our graph doesn't fit that profile. The local geometry confirms this root at x equals 2 only has a multiplicity of 2. This leaves a discrepancy. The function is degree 4, but our visual evidence only accounts for 2 degrees. This occurs because polynomials can contain factors that never cross the horizontal axis. In this case, a factor like x squared plus 1 creates structural bends in the line but yields no real roots. It exists entirely in the complex domain. This defines the limit of visual analysis. The sum of visible multiplicities is always less than or equal to the total degree, as complex invisible roots may always be influencing the shape of the graph.